What am I sharing?
Yes.
Desktop 1. I want both. Oh, let's try this.
The whole desktop or just
I think I just want, well, it's going to be full screen. So, oh, I can see over here what else is saying. So I'm good. Okay. So it's a 64-bit world, mostly. A couple years ago, 3 years ago, Apple decided that they would no longer support 32-bit anything. There was no obvious technical reason for that, but now that they've come up with their own chips, we see why they did it, because they're 64-bit only. So there was a fair amount of demand to move over to x64 from i386 architecture for SwiftForth, especially for the Mac, because the Mac would no longer run 32-bit programs. Linux still runs 32-bit programs if you have 32-bit libc support, which is not hard to install. So that's not a problem. And Windows looks like it's going to forever run 32-bit.
Like I said, Fedora or Fedora Linux, you can only get it with 64-bit. You have to.
Yeah, you just add this 32-bit libc to it. That's all you have to do.
You can run 32-bit on 64-bit.
Yeah, you can. Anyway, the biggest impetus to do this was just to get the Mac working on 64-bit. And at the time, I thought, oh, this is easy. I'll just make a copy of it and do a port. And it turned out to be not easy because of the way the source code was organized. So most of the work involved here, this is 3 years of work in 5 minutes. Most of the work was organizational, because we would like to have as much of our source code as possible be in common. What did that do? I'm trying to change slides. There we go. What's that stuff floating on top of it? How do I get rid of that? Can I? Is there a thing that says hide?
bread to make it go away.
I don't see anything on top.
You try it. Hide floating MIDI controls. Someone below it. Thank you so much. Okay, so starting with the old directory structure, this is how SwiftForth was organized. So if you've ever used it, you know this. And the most important part of this is from source on down. So I just popped open each of these trees and took a picture of it. At the top level of source, there's a directory for the kernel, and then a subdirectory for each of the platforms: Linux, macOS, Win32. And then at the higher level, we have the interactive development environment IDE section, each of which has those same subdirectories. Note that there's one intervening one, UL, for Unix-like, because the Linux and macOS themselves share an awful lot of code at that level. The problem was that interspersed throughout this whole directory structure was assembler code in i386. So my first mission was to figure out where I'm going to put all this, and then go through and find all of it and extract it. That sounds easy, right? Then I discovered that as hard as we tried back in 2001, when we did the first SwiftForth, to be portable, we kind of didn't really get the use of cell and cells for the cell size to be portable. And we started universally using cell to mean 4 bytes because it was a 32-bit implementation. And it turns out that's wrong. If you're interfacing with something like an operating system or a remote box sending you packets or something, and therein what happened to be your cell size, the system was coded to refer to those things as cells instead of 4s. So it took me a year to find all of those and move them. There are, it's crazy. I didn't do that all. It wasn't a solid year. I would work on this in dribs and drabs, and I would just have to take a mental health break for a while and then come back to it. So that's how that proceeded. So the first thing I did was I took all the architecture specific sections out and put them in a new section. Do you see this one nestled under source here? Oh, in the next slide, I highlighted it, called Arch for architecture. It contains a mirror for each of the architectures, i386, x64, and soon ARM64, and whatever else anyone wants to throw at me, of each of the below it. So it contains only the architecture specific things. So you can see under Arch, we have i386, and then a mirror image of the whole source tree, IDE, and its subdirectories, kernel and its subdirectories, one for x64 with IDE and its subdirectories, and kernel and its subdirectories. And that contains just the code specific portions to support this. And it turns out that that was a relatively small amount of source compared to all the source that's in, which is the way we like it, right? We want to keep it as top heavy as possible, with as little duplication as possible, because that's a maintenance nightmare. And you don't see that the ARM64 directory here yet because it's empty, but soon that will be populated. So the next thing to do is to consider the register model. In the i386 register model, the way we implemented the fourth machine was to always cache the top of stack and register EBX. I as the user pointer to the base of your user area. And in a traditional multitask system, those are all linked together. This is Windows or Linux or macOS, and we use threads or pthreads. And so that's the pointer of the area in extended memory that's allocated to your thread. And there you get all your user variables that you've come to know and love, things like base and here and so on. EDI is the base of SwiftForth memory because each of these OSs can technically load you wherever they to. You don't want to have absolute addresses anywhere in your image. You only want to have relative addresses, so everything is addressed relative and is based off of EDI. It also allows us to very easily write DLLs, dilibs, and .sos. EBP is the data stack pointer, the fourth data stack, and then ESP, which is the hardware stack that we use as the return stack pointer. It also contains frames that we build for catch and throw, for local variables, and for SWOOP data objects. So in the x64, it's very similar, except all the E's are now R's for the register names. So the same initial set, RBX, RSI, RDI, RBP, RSP. And because the x64 gives us another whole chunk of registers, some of which are used by the ABI for parameter passing when you make external function calls to the OS. So I try not to step on those, just less to save and restore. But the first thing I did was I took R14 and R15 for the loop index and limit, speed up loops, and man, did it speed up loops. Because previously they would have been held in the top two cells on the return stack. And then the next thing, one of our users who's beta testing for us said, wouldn't it be nice if the locals frame pointer was in a register instead of memory? So I moved that into a register. And he's a heavy locals user, and he reported a dramatic speed up by doing that. And if I do one more, it's probably going to be the SWOOP object frame pointer to point onto the stack. All of that, there wouldn't be as much of a speed up because there's so much calculation that goes on for those. So the other thing I discovered I had to do was completely rewrite the code optimizer, because a lot of our optimizations were dependent upon the use of immediate values. Some of our best optimizations had to do with literal something or something literal or literal something. And we immediate data moves anywhere we wanted to, and we could use immediates for ALU operations any way we wanted to, but not here. The only immediate 64 you get is an immediate 64 move to a register. You can't use immediate 64s for ALUs, and you can't move them into memory. So I had to rewrite the optimizer to do all that. This is just an example of the code optimizer and how it looks. So here's an unoptimized version of the word digit, which takes a binary value from 0 to 15 and converts it to a printable ASCII digit. Dupe, 9 greater than if, 7 plus then, character 0 plus. Here it is unoptimized, and I just divided it up. Each of those lines shows you all of the code in an unoptimized system for each of those pieces. So there's the code for dupe, the code to get your literal 9, 3 instructions, single instruction, which is a call to greater than, which is another whole chunk of instructions. If is the next 4 instructions, 7, the literal is 3 instructions, plus is 2 instructions, char 0 is 3, just like any literal, plus 2 more, and then the semicolon is just a return. So our code optimizer keeps a structure in memory that keeps track of everything in pairs built as a tree. It's basically a pinhole optimizer. When you turn the optimizer on, all of that turns into this, which is really nice. So you can use literals with ALU operations if they're 32-bit or less, so that condensed down. If that 9 had been a value that was greater than what could be represented in 32 bits, the optimizer would have moved that into a register and then done the compare with the register. That was what involved basically rewriting the whole optimizer. Very happy with the way it turned out. So, yeah.
With the caching of the loop variable, how does that work in terms of if you've got multiple layers of loops, or when you enter another word?
It pushes them.
Pushes them.
Yeah, pushes them at the beginning.
It has to.
Yeah, the code
saved or color saved. Is that force you to?
It's saved by you push them in do before you set them to the new loop and limited index.
So each time
and the word loop literally just assembles and pops. Yeah, I can show you an example. And also the optimizer will optimize the loop limit and index too, which is really nice. And they aren't strictly limited index. It's the top value, or the R14 value, is the original index minus the limit. And then what we call the limit is actually just that one with the high bit reversed, so that all you can do is, and you get overflow. So it works in both directions. That's a nice trick. The portability question came in, and I learned an awful lot about what we didn't do right about portability. Mostly has to do with the structures that you need to pass to the operating system to get any work done. This is true in all 3 platforms, but I'm going to use this Windows API structure because it's particularly nasty. Here is something we do when we define a Windows class, because you're about to spawn a new window and you want to make a Windows class. So you have to pass values in this structure. So here's the original definition from the header file. And you see all these things of uints and winprogs and ints and so on. And it turned out in the original 32-bit version, those were all 32-bit values. And we said, hey, we'll just use variable for that. We define SWOOP classes in our object-oriented thing so that you could have a class that matches the structure, and then you can just instantiate that class wherever you want. And the members of the class are exactly the members of the structure. And then you can just pass a pointer to the class instantiation to the call, and you're ready to go. And then you can reference them by name. So it turns out, going into the 64-bit world on Windows and also on macOS and Linux, that some of them are still 32-bit. They didn't just follow the cell size of the machine. So anything that was an int or a uint and some other things are 32-bit. So I call those L variables for long words. And this has some precedent. I looked around to see what other people are doing, and SwiftForth does something like this, and also SVFIG does something like this. And we also use some others that I'm going to show you a little bit later. And so I think that those are good candidates to become standardized since they're so widely used. So I didn't want to reinvent the wheel, because somebody told me once, if you reinvent the wheel, it turns out square and made of bricks. He's ignoring me. So this is what had to be done. Also, because they used to all be 32 bits and they started on a 32-bit boundary, they were naturally all packed. Not, and certain things need to be on the correct alignment. So if it's a 64-bit thing, it has to be on a 64-bit boundary. So I had to expand the class definition to handle the alignment. Or not, because some of the structures aren't packed. So there's a little mix. Anything that's shared any structure that's not only used internally, but externally, for example, the header of a BMP file, packed. Everything else is unpacked, even though technically it doesn't need to be. So for the memory access words, in order to maintain portability across all these systems so that the 32-bit fourth and the 64-bit fourth can talk about these structures in the same way, you need to be able to access 16-bit fields. We already had those. Those are the old W words, but you needed the 32-bit one. So this is where I borrowed this fourth in VFX, lstore, lfetch, and lfetch s in case you need to signed extend, because some of them do. And then the defining words L variable and W variable. That's it for that.
You're making me wonder if I could wrong. I used the S's and the W's, but I think I put the for the signed ones. I might have put the S at the front.
At the front, I just copied that from the way VFX did it, and I often tend to just use that as a subscript, so all the W words fall together. It's like a kind of a collation thing.
Do you recall, is G4 the other way, or is it
G4? I couldn't find the signed one, so maybe you can, and you'll tell me where it is, or I could ask Anton. Any questions? No. I put this out in beta test maybe 6 weeks ago. I sent out a mass email for anyone who has a SwiftForth subscription, and I got 80 responses back. Luckily, I'm not getting 80 sets of feedback because that's too much. It's a bit overwhelming. So the other thing I have to show you, and this will be real quick because my demo doesn't work. It turns out when you're running Zoom on here, if I go over to the virtual machine, I can't use the debug interface. I don't know what weird thing is. Somebody came to us recently and asked us to do a port of our SwiftX for the Raspberry Pi 2040. And we actually had a couple people ask about it, but someone's really going to use it. They're going to use a whole bunch of them. The RP2040 is a dual Cortex M0 Plus. It's a dual core. It runs at a clock speed of up to 133 megahertz. It's got 264K of embedded SRAM divided up into 6 banks. 4 of them are 64K, and you can allocate them such that each processor has exclusive access to a specific bank so that they're not blocking each other, because both of the cores have equal access to everything, to the peripheral. But if one core is going for one of them and the other core wants it, it'll get blocked, it'll get stalled. So you want to try to avoid that. So we allocate the stacks in separate space. It's got 30 multifunction GPIOs, 6 dedicated IOs for SPI flash, and that XIP thing means execute in place. There's a 16 megabyte space allocated for you to execute your program. And in hardware, it pulls chunks of the program into that space, into whatever the cache window size is, from the SPI flash, which is external. So this particular board I have here has 2 megabytes of SPI flash. And I just run in that space as if I were running in code space. And the performance hit on that is smaller than you think. I'm clocking it at 133 megahertz, and I benchmarked the execution in that space as just over 120 megahertz, which is absolutely. So the alternative would be you burn up all your RAM space and boot into the RAM and run in RAM if you want to run faster. I don't find any reason to do that.
Really? Have you been able to get the symmetric multiprocessing working?
What do you mean?
Well, you have 2 processors.
There's 2 cores in here, and the cores are sharing code space. So the entire kernel they're sharing, and then each of them can run whatever processes they need. But I give them separate stack space so they're not competing over memory cycles for stack, because that's going to slow them
So that
down.
would be asymmetric.
Yeah, it is. Yeah, it's totally asymmetric. Yeah.
Okay.
We did symmetric stuff in lockstep on a Cortex R5 for a multiplexer.
Question.
Oh, the question was, is it symmetric multi-core? And it's not.
Yeah, SMP,
Yeah. Yeah, multiprocessor. So this is the board. I'll show it to you here. I guess I can turn the camera on briefly, maybe. No, but I've lost all the controls.
Stop sharing. Turn the camera on.
I'm not sure how to get to there from here. Don't worry about it. For everyone watching, I'm holding up the board. It's a teeny tiny little Raspberry Pi Pico board. You can Google that, you'll find it. This board costs $4. $4. We have to add pins to it, so another 50 cents, I guess, for the pins. And then I am using the Sager J-Link as my debug interface. And if you don't have one of these and you do any kind of ARM work, you need one of these. This is the universal tool. This will get you into any ARM part that has a JTAG or SWD, serial wire debug interface on it. And it knows how to program their flash. All you do is point.
Right?
Hmm?
It's JTAG.
This is SWD, which is a single wire debug. It's JTAG over a single wire.
Okay.
Yeah, it's a bi-directional data line.
Right.
So the really great thing about these things is how cheap they are. All of that stuff in there, 70 cents a piece on a 70 cents each on a 3,000 piece tape reel, which is amazing. I think that's amazing. Here's just a quick of what it looks like inside. So you can see the bus fabric ties everything together. All the SRAM blocks are in there. The two cores are up at the top, and the two processor cores are tied together with this SIO, which is basically a FIFO that lets them talk to each other. And one of the things I know you're wondering is, how does this thing boot up if it has two cores? And what happens is core 0 has control when it starts up, and core 1 idles waiting on the FIFO. So core 0 gets everything started, and then it passes a few pieces of information over through the FIFO, and then core 1 goes off and does. So core 0 is essentially the master. Pretty cool. Okay, that's it for me. Thanks.
Very good. Very good. All right.
Is tell folks there'll be a little bit of a.
Get out of Zoom.
Yeah. I asked this before. But
Yes.
I have everybody here.
Sure.
Is SwiftForth endorsed by?
All right. Can you hear me now?
Yes.
Okay, what a relief. There's going to be.
Yeah, we kind of lost you for a second.
Agent plans. Brad, can you assure us that the camera is working for John? Which camera? Yeah, that one. That one. No screen to share, just a picture.
Okay,
I want
so
to do
that's
some
what it
ARM.
looks like in the world.
That's what it looks like in the world.
Brad?
Yeah.
Okay.
You're
So
on.
stand someplace where the camera can see you.
Right. Well, I want to get the
Where do you
camera.
want to be?
I was
Where
just
you
gonna-
want to be, and I'll point it at you.
Yeah, and this above me, the green. Can you get all that?